Hello and welcome to part two of this lecture on modular arithmetic. In this lecture, we'll cover uh, inverses in the Euclidean algorithm. And before we start, I just want to say that we have a handout on all of this that covers all this information. In fact, this lecture is actually based off of the handout. So I'll post the handout in the description below so that you can follow along with it. Okay, let me continue. All right, so what are inverses? The inverse of a number a modulo n is denoted by the a inverse, which is a to the negative 1 power, and is a number such that a to the negative 1 times a is congruent to 1 mod n. Before we move on, I just want to say, remember when I told you that division doesn't work in modular arithmetic? So let's say we want to solve the congruence. 3x is congruent to 2 mod 11. Well, we just can't divide by 3, and because we can't have fractions in modular arithmetic. However, there has to be a way to isolate the x. If we multiply by the inverse of 3, we'll get a 1 on the left-hand side, which will just leave us with x is congruent to the answer. Well, the only the only real trouble with inverses now is just to find the inverse. And in this case, we can just look through multiples to find them. So let's say that the inverse was k. So there must be some k, so that such that 3 times k is congruent to 1 mod 11, or it's equal to some multiple 11 plus 1. Well, that means 3 has to divide 11n plus 1. At this point, you can just go through multiples of 11 and see which one works. And the first multiple 11, just 11 plus 1 gives you 12, which is divisible by 3. So that gives you that k equals 4. And that's the inverse. Why? Let me show you. So let's say we multiply both sides of this congruence by 4. We would get 12x is congruent to 8 mod 11. However, 12 is congruent to 1 mod 11. So this is the same thing as x is congruent to 8 mod 11. So let's move on. Actually the last bit here, we will abbreviate the greatest common divisor of two numbers by GCD. If the greatest common divisor of two numbers is 1, then we say they're relatively prime or coprime. This can be more useful for the next slide, so let's move on to the next slide. And so the next slide says that an inverse of a modulo n exists if and only if a and n are relatively prime. Well, this should make some sense, since if they weren't relatively prime, that means a divides into n. And unless a is equal to 1, but you don't really need to care about that. That doesn't really matter. So that means a divides into n, and we can see the issue of why a divide a dividing into n is a problem. So if there's an inverse k for a such that ka was congruent to 1 modulo n, or it was congruent to uh, nc for some constant c plus 1, n times c plus n times some constant c plus 1. Well, that means that k, not k, sorry, a has to divide into nc plus 1. Well, a divides into nc. So that means for this to hold true, a must divide into 1. And that is obviously not true for any a greater than 1 that divides into n. So thus, an inverse of a modulo n exists if and only if a and n are relatively prime. So let's move on. Theorem 2.2. If a and n are relatively prime, then any two inverses of a modulo n are congruent modulo n. That is, if c and d are inverses of a, then c is congruent to d modulo n. I'm not going to write the modulo n from now on, just going to shorthand it with just the congruences so I can save some writing. So if they had two inverses c and d, that means ac is congruent to 1 and uh, dc and dA is congruent to 1 because they're inverses. Well, by, you know what, hold up. Let me write that as AD just for simplicity, because we'll keep the order. It'll be less confusing. So AD is congruent to 1. In part 1 of the lecture, we proved that the modular arithmetic has transitivity. So this actually shows us that AC is congruent to AD, modulo n. So let's multiply both sides of this congruence by C. That'll give you C times AC is equal to C times AD, but we can write that as D times AC. And why we write it like this is that AC is congruent to 1 modulo n. So this is just multiplying by 1 on either side. So this actually gives us C is congruent to D modulo n, and we have proven that. So usually when we refer to an inverse, since you want small inverse, you don't want to obviously find a big inverse. We usually refer to an inverse as being less than n, so it's something between 0 and n minus 1. So that is what we primarily refer to as an inverse, if you're wondering. Um, One last bit before I move on, I just want to say that calculating inverses gets tedious for larger values of a and n, and you can clearly see that. There are methods for finding it. There's the extended Euclidean algorithm, which you can search up online, or there is a lecture on it by Keenan, so you can check that out. And it's basically just a method to convert large inverses, and it does use the Euclidean algorithm, which we're going to cover in the next slide. And that's that. Uh, and also, that was all. So let's move on. The Euclidean algorithm and theorem 2.3, all it tells us is that GCD of AB is equal to GCD of A minus BB. This seems so simple, yet it is very powerful. The proof for this may seem a bit complex for those of you, which is an for those of you who are just looking at modular arithmetic for the first time. Since this is a beginner level lecture, I don't want to go into the proof of this. The handout does have a proof of this if you can follow along with it, and Keenan has proved it in the extended Euclidean algorithm lecture. So if you're interested, you can even search up the proof, but it is a fairly nice proof if you can follow through with it. Uh, but it is complicated for the beginner level if you're looking at this lecture. But I think you can probably understand it with some close reading, but we're not going to prove it today. So example of this will be in the problems. So we'll just move on with that. And so here are the problems. Oh, okay, so problem 2.1. Does the inverse of 5 modulo 10 exist? So we had this whole discussion on why if uh, the GCD of 5 and 10, which is equal to 5, is greater than 1. That means they're not relatively prime. And we said that if A and N are not if A and N are not relatively prime, then they don't have an inverse. So the answer to this is no, and we have proved that. All right, uh, let's go on. Compute the inverse of 7 modulo 18. This I'm just going to bash forward. So let's just bash 18n plus 1 and see which expression is divisible by 7. Well, if n equals 1, then this is 19, which is not divisible by 7. N equals 2, this is 36 plus 1, 37, not divisible by 7. You can see you're just adding 18 on here continuously, so if you add 18, 55, not divisible by 7. If you add another 18, that would be 73, not divisible by 7. If you add another 18, you would get 91, which is divisible by 7. This is equal to 7 times 13. So the inverse of 7 modulo 18 is just 13. Compute the greatest common divisor of 852 and 1737. Well, this is the Euclidean algorithm, and so remember that the Euclidean algorithm is GCD AB, and this will be your example problem basically for the Euclidean algorithm, is equal to GCD of A minus B, B. Basically, you're just subtracting from the larger number. So this is going to be equal to, I'm going to shorthand this with just parentheses, 852 and 1737 minus 852. 1 second. Sorry about that. Just want to make sure that I don't mess up this arithmetic. Uh, this is equal to 852 and 885, the greatest common divisor of the two. Well, we can perform the subtraction again, and this is going to give us 852 and 885 minus 852, which is going to be equal to 852 and the greatest common divisor 852 and 33. Now, you can perform this faster, the subtraction, by if it requires more than one multiple by just multiplying. So like uh, 33 will go into 852 multiple times. Actually, uh, 852 is equal to 33 times. I'm gonna write this out here. 852 is equal to 33 times 33 times 25. If you can't tell, I'm using a calculator. I don't want to mess up the arithmetic, so 33 times 25 is 825. So 852 minus 825 is 27. Obviously, this arithmetic is very easy to do by hand, but not on a computer. So it's equal to that. So we can just multiply. We can no, we can subtract 25 multiples of 33 from 852. So that's going to give us, if you do that subtraction, that's going to give us the greatest common divisor of 27 and 33, which we clearly know is 3. That's all good. Problem 2.4, the final problem. This is actually the first ever IMO problem. It's from the IMO 1959, which is the first ever IMO. And it's fairly simple with the Euclidean algorithm. So it is prove the fraction 21n plus 4 over 14n plus 3 is in simplest form. In other words, 21n plus 4 and 14n plus 3 are relatively prime. So we have to show that the greatest common divisor of the two is equal to 1. So once again, I'm going to shorthand it after this original writing. So get 21n plus 4 and 14n plus 3. So let's subtract 14n plus 3 from 21n plus 4. That's going to give us 21 minus 14 is 7, so 7n. 4 minus 3 is 1, so plus 1. And that is 14n plus 3. Let's do the same thing here. However, we can subtract two multiples of 7n plus 1, since 2 times 7n plus 1 is equal to 14n plus 2. So we can subtract 14n plus 2 from 14n plus 3, which is clearly just 1. So 7n plus 1, 1. Well, we have a 1 here. That means our greatest common divisor must be 1. And thus, the fraction is in simplest form. It is irreducible. And so we are done with this. And that is the end of part 2 of this lecture. If you have any questions, please do join our Discord and ask us on math help. And if you just need any help in general, or if you just want to solve cool problems, we have a problem of the day on our server and all of that. So Please do join if you're interested, and if you have any feedback on this presentation, please do let us know in the suggestions channel. Thank you, and have a great day.